Let's talk about something that affects literally everything you do online. Your messages, your money, all your secrets, they're all behind a digital lock. But what happens when someone builds a master key, a key that can open every single one of those locks? Well, that key is a quantum computer, and today we're going to look at the incredible new lock designed to stop it cold.
Right now, our entire world runs on a handful of encryption methods. You've got RSA, ECC, a few others, and they've been fantastic. But here's the thing, they all share one single fatal flaw. They're all based on math problems that a big enough quantum computer can solve almost instantly, using something called Shor's algorithm. So let's be really clear, the very foundation of our digital security is living on borrowed time.
So that's the big, scary question, right? If all the old locks are about to be broken, how do we forge a new one? How in the world do we protect ourselves from a machine that's basically designed to crack the very codes we rely on? To really get the solution, you have to appreciate the problem. See, a quantum computer isn't just a faster version of your laptop. It doesn't just try keys faster. It thinks in a completely different way. It's built to see hidden patterns in numbers, which just so happens to be the exact weak spot in all of our current encryption.
And this is the most important thing to understand. We can't just make our old keys longer or tweak the algorithms. That's like putting a bigger, stronger padlock on a flimsy wooden door. The solution has to be a whole new door, made out of a totally new material. We need to find a type of math that even a quantum computer looks at and says, nope, I got nothing.
So, what is this new unbreakable material? Well, it comes from a weird little corner of mathematics that deals with something called lattices. Now, I know it doesn't sound super exciting, but trust me, this is where we find the blueprints for a truly quantum-proof lock. Let's see how it works.
Okay, so what on earth is a lattice? Forget the jargon for a minute. At its heart, it's just a perfectly repeating grid of points. You know, like the corners on a checkerboard. The only difference is, in math, this grid can exist in any number of dimensions, not just two.
So for example, if you're in 2 dimensions and your only instructions are take one step right and take one step up, you're going to get a completely normal, boring square grid. Simple enough, right? This is our starting point. But now, this is where the magic trick comes in. What if I gave you a totally different kind of weird set of instructions? Like, go 2 steps right and go 1 step right and 2 steps up. You'd think you'd get a different grid, but no. You end up with the exact same set of points. And this is the whole secret. The same grid can be made from a good recipe and a bad one, and telling them apart is incredibly hard.
Now a little property. That's the whole ballgame. Because when we take this simple grid idea and we blast it into hundreds of dimensions, it stops looking like a grid and turns into an impossibly complex, chaotic maze.
The security of these lattices really comes down to 2 famously hard problems. The first is the shortest vector problem. It just asks, out of all these billions of points, find the 2 that are closest together. The second is the closest vector problem. I'm going to drop a point randomly in space, and you have to find which point on the grid it's nearest to. They sound almost childishly simple, but they're not. And here's why. We're not talking about 2 or 3 dimensions. Modern cryptographers are building these lattices in 512 or even 1024 dimensions. The complexity doesn't just add up, it grows exponentially. It gets out of hand fast.
You see, in that kind of high-dimensional space, our brains just can't even picture it. Our intuition about geometry completely breaks down. There are so many points, so many possibilities, that finding the single shortest path is like trying to find one specific grain of sand on every beach on Earth. No computer we know of, not classical, not even quantum, can solve that efficiently.
Okay, so we have this impossible math puzzle. That's great, but how do you actually turn it into something that could encrypt your email? Well, you add one more clever ingredient. A little bit of controlled randomness, a secret sauce called noise.
This whole idea is perfectly captured in something called learning with errors, or LWE. It's genius. So you start with a set of simple equations, the kind of thing a computer solves in his sleep. But then you add a tiny, tiny random error to the answers. And just like that, that tiny bit of noise makes the whole thing computationally impossible for an attacker to solve.
So what's really happening here is that the noise acts like a mathematical smokescreen. It's just enough to hide that perfect, clean geometry of the lattice from an attacker. It basically turns this abstract puzzle into a practical code that we can actually use to send secrets. All right, let's bring it all back home. We have these impossibly complex mazes, camouflaged with a little bit of mathematical noise. Why is this our best hope? What does this actually mean for keeping your data safe in the future?
Well, that goes back to what quantum computers are good at. They're amazing pattern finders. And our old crypto is full of the exact kind of neat, repeating patterns that they love. Lattices, on the other hand, are messy. They're based on chaotic, high-dimensional geometry. And right now, there are no known patterns, no shortcuts that a quantum computer can exploit to break them.
And this table just lays it all out perfectly. We are in the middle of a massive shift. We're moving away from a foundation of number theory, which we know is broken, to a new foundation of high-dimensional geometry, which we believe is secure. We are literally swapping out household names like RSA for new standards like CRYSTALS-Kyber. This isn't just an update, it's a whole new architecture for security.
So, at the end of the day, these strange, mind-bending, multidimensional grids are so much more than a mathematical curiosity. They are genuinely one of our best bets for building a digital world that can actually survive the coming quantum revolution. They're not just an idea, they are the foundation for the next era of privacy.